Live stream my presentation about application embedded zero trust. I don't have a high quality recording of it, one where you can see all little bits and bobbles and pretty slides. So here it is. I'm Clint. I work on the Ziti project, and I'm going to talk to you today about application embedded zero trust. So every open source project worth its salt requires a little logo or a mascot. And we have a mascot, and his name is Ziggy. He's down here in the lower right-hand corner. You can go online and you can find Ziggy on Twitter and lots of different places. And if you're interested, go and check him out. All right, so why are we here? We're here to talk about zero trust, right? Usually when I present at conferences, this is the line or the look that I get from lots of people. What is zero trust? What does it even mean to be zero trust? Zero trust is kind of a marketing buzzword. It's kind of been abused quite a bit now. So usually when you talk about zero trust, you'll get some looks like this. But hopefully after watching this presentation, maybe you'll have a different opinion. Anybody know what this particular image represents? This image represents the longest duration or destination that you can walk across the earth. So you can start in the southern tip of Africa and finish in the northeastern part of Asia. And it's a very long trip, obviously. And so this is illustrative of your path to zero trust, particularly to your path to application embedded zero trust. So when we start talking about application embedded zero trust, we'll start thinking about the differences between what zero trust really means, where you draw the lines of zero trust, and you'll understand later why I put up this slide, because it is a journey getting toward zero trust. So this is what the presentation is all about. It's a current network setup we'll look at. We'll look at an overview of zero trust. We'll see some application embedded superpowers, and then we'll look at some of the applications that we've already made that you can go take a look at. So let's get started and let's talk about the current state of the art when it comes to networking security. Here we have a basic network. In the lower left-hand corner, you might have a corporate office. In the top, you have a house like the house I'm in right now. In the bottom right, you'll have some cars, or you'll have people on their cell phones, and you have wireless networks, right? So this is just a basic overview of any generic corporate network. And what are these for? Well, they're for the express purpose of sending data, right? So you want to be able to send your data in between your devices. And you'll notice now the network is converted into a little castle and a little moat and little drawbridges, represented by a firewall. And so generally speaking, in the classic sense of network security, you think about making these secure areas, these secure networks, these private networks, which are considered trusted. Once you get onto that network, it's acceptable to send traffic from one device to another device because it's a trusted network. And this has served us really well for a long time, but it hasn't been perfect forever. Long time ago, back in the day, we used to send traffic using HTTP, which is an unencrypted protocol, or we would use Telnet or any other types of unencrypted protocols. And so we said, hey, this unfettered access to all of my devices on my network is probably not a good idea. And anybody who can listen can just see all this stuff right in the clear. So what did we do? Well, we said, hey, let's put a little lock icon on all these network connections, and let's consider them secure. And we'll use some sort of transport layer security, or SSL, or HTTPS, or however you want to think about it. So that's what we did. And people said, hey, that was a good idea. Problem solved. We can just go home now. We don't have to worry about security anymore. This is it. This is state of the art. And so this was so successful that there were two interesting projects, at least, that came out of it. One of which was called HTTPS Everywhere, and one of which was, or is, the certificate authority known as Let's Encrypt. So HTTPS Anywhere, from the Electronic Frontier Foundation, its whole job in life back in these dark ages was to see, If you were going to an HTTP endpoint, it would check, it would see if there was an HTTPS endpoint, and if there was, it would just silently change you over to HTTPS. Then there was Let's Encrypt. Let's Encrypt came along and said, hey, all these people want to do all this secure stuff, but getting a certificate costs money, and that's kind of a bummer. So what if we make it easy and free for people to get these certificates, to have these secure connections? And so that was really helpful. HTTPS everywhere was actually so successful that all major browsers nowadays do exactly this. They will automatically upgrade you, and it's so successful that the Electronic Frontier Foundation no longer needs to support HTTPS everywhere. It's just now native. Okay, so what is wrong with the wall and the moat classic idea? Well, the big problem is that if you are an attacker, if you get onto that particular network, then what happens if somebody uses a weak password or they have a 0-day exploit or something? Well, that attacker can just attack our target of opportunity, and all of a sudden you have a compromised laptop or server or whatever. In this case, we're going to keep attacking this particular laptop. So just by getting over the walls, through the gate, over the moat, however you want to think about it, just getting inside of that special protected network gives you all of the access that you require in order to send traffic to some target of opportunity. In case you aren't aware, this is exactly how a VPN works. Once you connect to the VPN, you're basically able to connect to whatever you want inside of that VPN. I personally have never been on one that does not work this way. I'm sure there are some more advanced VPNs that are out there that do allow you to do a bit of segmentation, where you carve off parts of your network. Speaking of segmentation, that's exactly what people decided. It's like, hey, we're using TLS everywhere, and that's great, but we've got this bad guy, and he wants to get at that laptop down in the lower left again. So what are we going to do? Well, we'll take Ziggy and we'll put him in a cool little cop outfit, and we'll make him the network cop. And so this is called segmentation. Basically, you're carving up your network into two different pieces, and you say, hey, everybody who's on the left can't talk to anybody on the right. So when that attacker tries to send his data, he's discouraged because he can't send the data to the attacker. So what happens? Well, the attacker is going to look around and try to find somebody. What's he going to try to find? He's going to try to find that laptop that does need access to both. Maybe it's developer, maybe it's QA engineer, maybe it's HR person who has to have access to both networks. We don't know, we don't care, but attackers are resolute in their persistence. So what are they going to do? Well, they'll just compromise that laptop, move right along, and then attack the actual laptop that they want to. They'll move horizontally, even though we've tried to put up a block. And now, mind you, the more blocks we can put up, obviously that's the better, right? So this is where some overview concepts of zero trust come in. So let's take a look. We're going to go back to our basic network now, and we're not going to use the castles and the walls. And what we'll do is we'll come up with this idea, and we'll call it device identity. So if you don't understand what device identity means, it basically is a situation where your network is smart enough to know what device is trying to connect to that network. That's great, because even if the device attaches to the physical network, the network is smart enough to know that there's a strong identity that the device has to present to the network. And if you don't present that strong identity, usually some sort of certificate, something that's cryptographically verifiable, is what goes into that identity. If you don't present that identity, then you're not going to be able to get onto the network. Um, Creating that identity is actually a relatively complex process. It's not so hard once you understand what it is and how it works, but getting there might be a bit of a challenge. So there's a whole entire blog series written by one of our engineers. It's great. You can go out and you can read the 5-part blog series about bootstrapping trust. Here's a quick little overview of how it works if you're interested. So device identity. Now our attacker's back. We have a network that knows what devices are attaching to that network, and it won't let devices on the network which don't present that identity. So here we have our attacker. They plug into the Ethernet and they start sending their payload, but bam, the network says, no, you can't send data. You weren't even authorized. You can't even send this data. Well, that's fantastic. But what happens if our attacker decides to find somebody who does have the proper identity? So here they've found a developer or QA or HR person who has a proper identity. And now what do? They send their data onto the network and they compromise that target like they're trying to do. Okay, well, great. We're putting up more and more hurdles here. But let's add another hurdle. Let's add this hurdle called least privilege. Least privilege is a situation where the network understands what devices are allowed to connect to other devices, or in OpenZiti parlance, what identities are allowed to connect to other identities. So here we have the same network, but this network is smart. It knows that identity that is being used, and it knows that the identity that's being used is not allowed, it's not permitted to send data to the target of opportunity. So what happens? The attacker sends its data, it gets to the network, and the network says, nope, you're not permitted to send that data. Now, of course, if that developer or that QA person does have a strong identity and that strong identity is allowed to communicate on the network, well, then you have a different problem. Now you have the same exact issues before. The attacker will be able to send the payload to the destination, but we're just keep adding layers, and we're adding more layers of defense. The more layers of defense, the harder it is to actually attack, the better your security posture becomes. Speaking of postures, one more thing you can do is you can add continuous authentication or authorization. Here we have these things called posture checks. And so what you can do is you can enable a posture check that says, Clint has to have passed his MFA check. And if he doesn't pass MFA, then when he tries to send data, the network will say, nope, you haven't passed MFA. You can't send this data. So these posture checks are a way of doing that continual authorization. So great. That's some zero trust concepts overview. Let's go ahead and now talk about embedding zero trust in applications. So let's go right into application embedded zero trust. You'll hear this term of an overlay network. Let's get this out of the way. So what is an overlay network? Well, generally speaking, when you think of a network, lots of people think about the internet. So we're going to just use the internet and we're going to call it something different. We're going to call it the Ziti overlay network. This is great because anybody who has commodity-based internet will be able to have a secure zero trust overlay network. So that's what we're going to build here with OpenZiti. An overlay network is composed of a controller. The controller does interesting things like authorize incoming connections. It'll do things like inform you of what services you have available to you. It'll do controller type things. Then there's going to be things we call routers. And routers are useful because routers are their job in life is to transfer data, but they're not very useful unless there are some connections. So we're going to head and connect everything together. All these routers will form a full overlay mesh, but it won't just be a regular connection or a standard TLS connection. It's going to be mutual TLS, which is great, right? Now, when the router connects to another router, each router has to verify the person connecting is who they say they are through that same idea of a strong identity. I'm going to take away these little lock icons because it makes the diagram busy. And then all this is for one purpose, which is to create or to allow edge connections onto these routers. So here we have a computer on the left and some API on the right. We have our edge routers, we have our network, and that's all for the express purpose of just sending data. We need to shuffle those bits as fast as we can. The overlay network takes care of the shuffling of the bits. The edge SDKs or endpoints take care of the secure overlay, and you have an overlay network. There's basically three types of zero trust access, at least that I think of right now. I don't know if there's more, but these are the three I think about. On the top, you have zero trust network access, host access, and application access. Let's take a look at each. Zero trust network access, or ZD network access, is basically between router and router. So in this diagram, you can see that's your zero trust zone. Everything to the left of the first router or the right of the second router, this is your trusted zone. You trust your private network. This is like the castle in the moat idea. you do have to trust your local network. You do have to trust your devices. You have to trust your device host network and the application itself. So this is your trust zone. Here's your zero trust, and that's network access. Let's go ahead and look at host access. Host access, much stronger. Zero trust host access involves a identity of some kind and a agent of some kind that runs on your device, represented by the little circles here. So now you have zero trust host access. Great. You don't trust the local network. You can leave your firewall totally blocked on both the server and the client. Awesome. That's host access. We can go one step farther though, and we can go into application access. Here you'll notice we no longer trust the host network. The client, if you will, is an SDK baked into the application on either side, whether it be on the server or on the device. A really important aspect, let me go back, of zero trust access is you can mix and you can match each of these. If you wanted network access on your server side and application access on your client side, or network access on your client side and application access on your server side, you can definitely do that. So don't think that it's one or the other. And finally, if you wanted to, you can actually extend your range of trust or non-trust a little bit further by adding a hardware root of trust, which allows you to trust even less of the operating system itself. Now, all that hardware key is what you can use in order to have even a bit finer, not finer, but a bit more less, a bit less trust. However you want to think about it. Okay. So now let's go back to our little diagram. We're going to focus on our attacker and we're going to focus on our target. And so what we're going to do now is we're going to talk about application embedded zero trust. And to do that, we're going to take a box, which is representing an application. We're going to take an OpenZiti SDK and we're going to cram it inside that box. And after we've crammed it inside the box, we're going to put a little lock icon on the box. And now you know that application is safe and secure because it's got a lock icon, right? And then what we're going to do is we're going to deliver that application to various devices. Now you'll have zero trust application embedded security in your application itself in these little secure applications. All right. Why is that neat? That's neat because here we've got three kinds of applications: SCP, SQL, FTP. If For those who don't know, FTP is one of those insecure protocols. Does not have encryption on it. That's why SCP and SFTP exist nowadays. Secure transport, secure copy. So here, what's great about this is because now you can see the purple lines. When the SCP app wants to send data to the SCP app, yeah, great. It works just fine. When the SQL app wants to send SQL traffic, that works just fine too. We have application embedded zero trust. The application only knows how to talk to the services it's configured to talk to. FTP can talk to FTP. Everything is great. Now, what happens if the SCP app, say, tries to send FTP data? Well, just like before, the application doesn't know how to send traffic to FTP, so it can't even actually do it. The same will be true for SQL Server trying to send FTP or SCP data. It just doesn't work. And this is where OpenZiti comes in. Coming back to this slide, it's destination. This seems like my slide deck may be out of order, but that's okay. It's a long destination. So, I remember why. And the reason why it's a long destination, so we make these things we call tunneling applications. Tunneling applications are cool because they're not application embedded, but this just goes to part of your journey. As you start down the path towards zero trust, you're going to need these clients, these agents that we talked about. And so you can get agents for all your operating systems. The reason why this is neat is because tunneling applications have a particular feature that is fantastic, which is totally private DNS. So with a tunneling application, which is a special version of application embedded zero trust, an application that the OpenZiti team has made, you can intercept addresses that don't actually exist. So if you wanted to go to Bodie McBoatface or Fluffernutter or Vault.zd. You can do all that with an OpenZD tunneling application. And what's really cool about this too is that this is all authenticated. So if you don't have access to the OpenZD overlay network, then none of these DNS requests make any sense. Also notice they're not even valid top level domains either. And because they're not valid top level domains, it's pretty exciting because you can now be guaranteed that your domains will not resolve and cannot resolve unless you're on that OpenZD network, which is pretty neat. All right, now we can talk about the superpowers of application embedded zero trust. If you haven't seen, the car on the top is called the Beast. It is the limousine that the president of the United States uses to drive around in. It's got all kinds of great security features: bulletproof doors, bulletproof windows, blast proof windows and doors, tires that run flat, all kinds of great security. But you'd never know it just by looking at it. If you take a look at the bottom picture, this is more of the Mad Max style of security, where you're bolting your security onto your car. So here at the OpenZD project, we'll say things like build it in, don't bolt it on. And this is what we mean. When you build it in, you have security that's baked into your application. It's hidden from attackers. People don't know where the chinks in the armor are. They don't know how to attack. They don't know what to look for versus the Mad Max style. So when you build security into your application, you're basically taking the beast approach versus the Mad Max approach. Another superpower, in my opinion, is addressability. So on the top, if you're lucky and you have IP addresses, then when a developer wants to send data to my application server, the developer can go ahead and enter a DNS name. That's great, my application server. But that application server is going to turn into some IP address, and it's going to travel over the internet or network or whatever, get the load balancers. And then as a developer, if you're super lucky, it's, a totally public service on a private IP address from one particular individual. But so many times the IP address that comes in, first of all, isn't forwarded to you. So the load balancer doesn't forward it. Now you don't even know what the source IP address was, or it's from an exit IP for a company like, Microsoft or Facebook or somebody huge. So now there's 10,000 or 100,000 different people who might be behind that one particular IP address. So it doesn't do you any good. Contrast that to an OpenZD overlay where you have the ability to address an actual identity. So you can say, hey, this message comes from Clint. Actually, you don't even have to say that because your source identity is cryptographically verifiable. You know that it's Clint as the receiver of the message. You know that it's going to Prometheus, the name of the identity, and Prometheus is able to know that it comes from Clint. There's um, no worry that you have more than one identity being identified, and no worry that the caller doesn't know exactly where this is going to, or that there's some intermediary in between. That's pretty cool. Another superpower that I don't think gets enough credit is that it's just an SDK. So you can bake that SDK into your application, and that application can be your server. All too often, we don't think about the server side. We think about that as the most protected network. That's the one where our network engineers and our DevOps people have painstakingly secured it, and we don't have to worry about that. But really, we should, right? In fact, I think this is such an interesting and great superpower. I put this slide in here twice now, and I call it out with these pretty big firewalls and whatnot. So notice that there's no inbound firewall rule in this case. So because I've been able to add zero trust into my application at the server, I no longer have a firewall rule necessary. That's really powerful. Why is that so powerful? Well, about this time last year, there was this thing that ran around the internet called Log4Shell. I don't know if you've heard of it, but if you haven't, go check it out because it's neat. And what happened there? Well, attackers found those Log4Shell servers, compromised them, and then do what attackers do and just moved along trying to establish a foothold, trying to infect other servers in the protected domain. Well, if you had an OpenZD overlay network, that attacker would be stopped immediately. They simply can't access the log4j server. There's nothing to attack. There's no hole in the firewall. Now, those of you who are astute will notice, just like before, if the attacker did find a laptop that did have the identity, sure, you'd be able to still exploit log4j, log4shell. But again, we're always adding defense in depth, adding layers. It's one more piece of difficulty for an attacker to do to get that actual strong identity. Because they have to have that strong identity. They have to compromise that laptop or uh, collect that strong identity somehow. And then if you add MFA on top of that, you had yet another defense in depth. So not totally infallible, but pretty darn good. And also, there was another one. Spring Framework had one. It was a 9.8. 9.8s are pretty bad. That's a CVE, a critical vulnerability and exploit. You want to make sure anything over a 9 you address immediately. Another cool power, being from the server side, is that your server can just reach out and talk to your clients. Lots of times in the IoT space, you get this kind of functionality from the platform, and it's sometimes implemented in the form of WebSockets or long polling, HTTP long polling, or short polling. But being able to reach out from the server and to directly contact a client addressably using those strong identities is a really cool superpower. So cool, in fact, that you can even do this. Again, remember, it's just code from a Lambda. You don't actually need a server. You could do this in a serverless environment too, which is also neat. We had an intern last year, this year, do exactly this. Took an Amazon Lambda, crammed our Python SDK into it, and used that Python SDK to send secure chat messages to our chat server. Pretty good stuff. Another great superpower, end-to-end encryption. You get this just out of the gate with an OpenZD overlay network. Um, in the CSDK, this will use something like ChaCha20 Poly 1305, which is from libsodium. And that's nice because it's designed for low power devices. So end-to-end encryption, you get that by default. You have to go out of your way to turn off end-to-end encryption. Another great superpowers, port inference. Go to any network, attach to the router and start looking at what kind of traffic happens, and you'll get lots and lots of interesting information. Who's going where, who's doing what on what service. Really useful for an attacker. But if you were to synthesize all of these services over a single port, like what you can do with OpenZD, then all your ports can belong to OpenZD. Now, this person who's showing up and trying to gain information by sniffing your network is going to be a little disappointed because everything will look like 443 to them. Going back to continual authorization, we talked a little bit about that earlier. Really cool superpower. If you have a Windows device, or I guess Linux or Mac, if they join a domain, you want to check that you're on the right domain, you can do that. You can check that the MAC address of the Ethernet card is the one that you expect it to be, that the OS is patched to the right version that you expect. MFA, I talked about, multi-factor auth, process checking is the virus scanner running, those sorts of things. Cool stuff. A self-healing mesh network is a vital part of a zero trust overlay, in my opinion. OpenZD has a great one, which will allow you to have additional scalability as well as redundancy, and smart enough to get you from the client side to the server side as fast as possible. That's great. Another great superpower is how easy it is. Here you can see some Java on the left before ZD and after ZD. Um, I've been presenting this live now, which is nice because usually I can shrink it down and only focus on the bits that are important. But now I can make it even bigger, and I have to make it even bigger so people can read it. Notice here, before, you are listening on the underlay. You have to know what port number you plan on listening on. You have to know what IP address you plan to listen on. This is great all the way up until, as a developer, you deploy your application thinking that you're listening on port 443. or 8443, when the ops guy decides that port 443 will be port mapped to 8443, and then you don't get any traffic to your server because you don't know why your server's not getting traffic, because somebody thought it was a good idea to change port 443 to 8443 or whatever. Well, you don't have to worry about any of that after. With Ziti, you just say, I'd like to bind this service, and you just bind it. This is one of my favorite superpowers of an OpenZT overlay. I called it implicit MFA. That whole enrollment process I talked about earlier is a really important process and ends up with that strong identity. If you have that strong identity on your computer, then even if somebody were to get your password, they are not able to access the overlay network to use that password. So you have implicit MFA without having, the standard two file that everybody's used to enter your 6-digit code kind of thing. You just have implicit MFA if you have an identity on your local computer that has been enrolled into an OpenZT overlay network. And so that's really awesome. I don't have a demo, so I'm gonna have to skip this next one. I'm not ready for that. This is what it did. This is the Vault demo. I did this fun demo before. All right, so let's look at some existing Zetifications. And Zetifications where you take a Zero Trust SDK and you bake it into an application, and now you have Zetified that application. We do that and we put them up on this place we call the OpenZT Test Kitchen. Here's Ziggy in his chef outfit, which is nice. And so you can go out to the test kitchen and check out any of these applications themselves, play with them, see if you like them. Have a look. Let's just go over a few of them. ZSSH. You might think to yourself, why are you bothering with SSH? Isn't SSH a solved problem? Lots of people are solving this problem again now because port 22 is open, right? So having port 22 not open to the world, that would be better. So why don't we just use a zero trust overlay network, one which doesn't require a port that's open? And now we can't even access our SSH machine without having access to the zero trust overlay network. That's great. On top of that, SSH is no longer attackable. If SSH ever had some sort of vulnerability, I would imagine most people on the planet would scramble very, very quickly to go patch their SSH servers because that would be terrible. But if your server is not listening on the open internet, then you have a bit more time to go ahead and get your patches out. You don't have to scramble quite as much. So that's why we made ZSSH. So you can actually use ZSSH to attach to your SSH machine, in this case, application embedded, without the need of having a client other than ZSSH. You don't need that agent that we talked about. SCP, same sort of thing. You can do the same sort of stuff with SSH as you can with ZSSH. It'll let you transfer data. Pretty neat stuff. You can see that SSH looks, or ZSSH looks just like SSH. You have the name of the executable, the strong identity you want to use, the service name you want to attach to, and then who the remote user is and what that target identity is. Notice you're SSHing to the identity. You don't SSH to an IP address or host name. That's cool. Same is true for SCP. Same sort of idea. Looks just like ZSCP looks just like SCP. Mattermost is our chat app. When we want to talk to one another, we use Mattermost. And when we get commits from our SCM, in this case, GitHub, well, I need a capital H there. We needed a Zetified webhook. So you can go out and get a Zetified webhook. And then when somebody makes a pull request, you get a little Ziggy who's dabbing that says, hey, that pull request has been approved. Yay. Generified ZDBC. This is really cool too. This is a project where we have a different kind of Zetification. This one is from Java. It allows plugins, which is nice. And so we have basically wrapped JDBC in a way that doesn't require you to update the ZDBC driver when you update your Postgres driver or Oracle or MySQL or whatever, which is really neat. So then you can do things like go into data grip, define a Zetified Oracle connection, add a URL down here, and now you can just access the database without the need of an agent, which is really cool. Here it is blown up again. Remember, I have to display this to people in the real world now, so you get to see the small screen and the big screen. Here's just proof. It doesn't have to only be Oracle. It also works with Postgres. It works with every database that we've tried so far. So you just define your connection, and then you don't need to turn on, quote unquote, turn on the VPN in order to support your database. You just run your data grip query, and you're running it against production in a secure way. There's a nice little article posted by Todd out here you can go check out. This is about Spring Boot, not so much ZDBC. kubectl, Helm Z, Prometheus, all in the same kind of ball of wax. Kubernetes is a big thing nowadays. Having your Kubernetes control plane not be on the open internet is a really good idea. So if you can, you should hide it. Oracle does a good job. They let you use an SSH bastion, but even easier is to use a zero trust overlay like OpenZiti and get at it that way. Then if you do that, you can either use kubectl the way you're used to, or you can use kubectl, the Zitified version of kubectl, and then you don't need that VPN agent again because we're application embedded. So that's cool. Check out kubectl or Zetel. Helm Z, same idea. Prometheus. Prometheus has an interesting problem. Prometheus wants to go out and scrape information. So here's like a typical Prometheus install. You have a Prometheus server. You have another Prometheus server, or you have a target that you want Prometheus to go and access and scrape. So Prometheus is allowed to talk to the Kubernetes control plane. Prometheus is allowed to talk to these Prometheus endpoints. And you want that Prometheus somewhere, maybe in your private network or whatever. So you've got some listening ports on the wide open internet. Maybe you've got them locked down to IP addresses. We already talked about how IP addresses are better than nothing, but not as good as a zero trust overlay. Instead, you can use a zero trust overlay like OpenZiti, and now you have no listening ports whatsoever. You have access provided via a Ziti pod or zero trust SDK. You have access via the overlay and not the underlay. So you have Zitified traffic. When I Zitified Prometheus, one of the things I thought was really neat, if you'll look over here, this is the fully Zitified Prometheus. It came with this application called config map reload, and I had to rewrite config map reload, or I had to add Ziti to it, because this thing's job in life is to watch the Kubernetes config map, and when it changes, it tells Prometheus to reload from the config map. But because I had Zitified Prometheus, and because Prometheus had no listening ports, this container wasn't even allowed to send a message to the Prometheus server. There was no port listening on the underlay for this to use. So I had to Zitify the config map reloader. So that was neat. Ansible, working on a Zitified Ansible. We've seen that work. I don't know if we have a blog post about it just yet, but I know we're working on it. Spiffy and Spire integration. If you're interested, you can go to Ziti TV and see a nice video where Andrew and I demonstrated Spiffy and Spire integrating seamlessly with Ziti. That was really cool. And then there's this other new neat one called Zitify that Eugene Kobyakov has been making. This is really nice because Zitify allows you to basically get application embedded zero trust without recompiling an application. It doesn't work with all of them, but it works with quite a few of them. Right now limited to Linux because it uses this LD preload trick, which is a way of injecting your code or the code that you want ahead of the system libraries. So what Eugene did is he tapped into the socket API, things like bind and accept and listen, and now you can run a little shell script wrapper that Zitifies your application without you having to recompile it, which is really neat. All right. Why is this important? Well, this is an old from 2021. Look at that, so old. But let me highlight why. Zero trust appears 11 times on this paper. In fact, I get this diagram from the bottom URL, but they've got a nice new URL I noticed when I was redoing this, zerotrust.cyber.gov. Check it out. Talks about the strong identity, talks about workload authentication, talks about data. Definitely worth it. Zero trust is coming. It is the future. I really do believe that. At this point, you're saying, "How do I get OpenZiti? What do I do? It's so amazing. Let me put it in a shopping cart. Let me go get it. How do I do that?" Well, you go out to openziti.github.io and you'll see a landing page that looks like this. Got our docs link up there. You can get OpenZiti and host it yourself. Number two, you can try out this thing we call Zeds. Number three, you can try CloudZiti, which is a free tier of OpenZiti hosted by NetFoundry. And then you can always grow past that as well if you want. Number five, links to Discourse and GitHub. Go out there. Here's all of our socials if you're interested in them. We have a YouTube channel. We do ZD TVs all the time. In fact, maybe you're watching this on ZD TV right now. In fact, let me do this. Let me unmaximize that. Bring my hey, there I am. I've been here the whole time, really. We have the Test Kitchen. We have OpenZiggy on Twitter. We have OpenZD on Twitter, GitHub, Discourse. Check us out. And the whole reason why I like giving this presentation is for one thing, and that is for stars. Because as we all know, stars are the judgment of a project and how great a project is. In fact, I forgot to update this slide. We're all the way up to 774, I think, right now, as of December 8th, 2022. So maybe if you're watching this and you think this project sounds neat and fun and cool, go on out and give us a star. That's really what it's all about. And that is the whole presentation. So hopefully you found this interesting and exciting. And if you have any questions, hit me up on the discourse. And until the next time, I'll see you. Bye. End stream.